this chapter 4 is going to be a preparation for the chapter on Laplace transforms. Laplace transform by definition is an integral from 0 to infinity f of t e to the power minus st dt. So, in the very definition you see an improper integral appearing. So, first I would like to briefly review the basic concepts on improper integrals, and then we shall study in some detail the gamma and the beta functions. These are two special functions which appear in many formulas, and this will be required in many formulas in Laplace transforms. It will also be required in the definition of Bessel's function. For example, the Bessel's function Jpx in its very by definition involves a gamma function. There is a gamma p appearing in the definition of the Bessel's function, and the gamma function appears in numerous formulas in engineering, and I think it deserves a chapter to itself. So, I think this improper integrals, beta function and gamma function, all these things are clubbed as one single chapter. So, that is the title of the chapter. The chapter is chapter 4, improper integrals and the beta and gamma functions. So, this will engage us for the next half an hour, and then probably the whole of the next lecture, and then let's see. All right. Okay. So, what is a improper integral? Okay. So, do not write all these things. I mean, so as I said, this chapter is regarded as a preparatory for the study of Laplace transforms. Okay. Now, how do you define the Riemann integral? The Riemann integral a to b f t dt. The function first of all is required to be bounded, and the interval a b has to be bounded. A is a real number, b is a real number, and there is a closed bounded interval a b. And then you take partitions of this interval, and you take the supremum and the infimum over each subinterval, take the upper Riemann sum and the lower Riemann sum. The thing completely becomes meaningless as soon as the function is unbounded. Okay. So, we have to now worry about how to salvage the situation when we have unbounded functions, or when the interval becomes large and unbounded. There are two situations: the function itself can become unbounded, or the interval can become unbounded, or a combination thereof. So, accordingly we have an improper integral of type 1, improper integral of type 2, improper integral of type 3, which is the combination of type 1 and type 2. That is the rough classification of improper integrals. So, now let us assume that we have a function f from the infinite interval a comma infinity. So, closed at a. So, f of a is finite, right, and the interval is unbounded. It is a real valued function. So, well, it can be real valued function, but still it can be unbounded. So, that is another problem. Suppose I take f of x to be root of 1 over root x. Say a is 0, f of x equal to 1 over root x when x is not equal to 0, equal to 1 when x is 0. Function is real value. It is defined from closed interval 0 to infinity, and it is unbounded. And this is a problem. So, we are not going to be. So, we have to first make an assumption that the function is going to be assumed to be Riemann integrable over every subinterval a to t, closed on a and closed at t, which means that example I gave you is out. That example I gave you is out. 1 over root x is not bounded. When I say that the function f is Riemann integrable over closed interval a comma t, it means the function is bounded on every closed interval a comma t. Right. So, that is already built into the statement that f is Riemann integrable, the boundedness assumption. And then we want to define integral a to infinity f t dt. The most natural thing to do would be to define it to be the limit as t tends to infinity a to t f t dt, correct, provided the limit exists. So, do not write everything, because there is too much to write, and you just understand this. The definition is very natural, and much of what we are going to do is very natural and very straightforward, and it is there in every book. You will find this in every book, but for completeness I am doing it here. I can't just say that I will assume you know the theory of improper integrals and beta gamma functions. That would be too much to expect. So just for completeness, everything is here, but no need to write everything, just try to take it all in. Similarly, you can define the integral minus infinity to a ft dt, where the function is defined on minus infinity to interval a closed at the a, and the function is assumed to be Riemann integrable on every subinterval t comma a, and I will allow the t to go to minus infinity. That is the obvious way to define the other one. Okay. And if you have a function from R to R, then how do I define the integral from minus infinity to plus infinity? It is defined to be the integral from minus infinity to a plus integral from a to infinity, and the stipulation is that both the pieces exist as in the sense described above, correct. So this is so this takes care of the definitions. Okay. So which requires that both the pieces should exist. Now if the limit exists, terminology, if the limit exists, we say that the improper integral converges, otherwise we will say that the improper integral diverges. Standard terminology, standard words and phrases that we are going to use throughout. So we should have a clear understanding of what these phrases mean, so it is all spelled out for you. Then the notion of absolute and conditional convergence, that is another standard phrase and we should understand its meaning. Integral a to infinity ft dt is said to be absolutely convergent if the integral of the absolute value converges. If integral a to infinity absolute ft dt converges, then you would say that the integral is absolutely convergent. Okay. And otherwise we would say it is conditionally convergent, is that right? If integral of ft dt converges but not absolutely, then we will say it is a conditionally convergent integral, all right. So now some standard symbolisms, when f is positive, non-negative, and when the integral a to infinity ft dt converges, instead of saying the integral converges or the improper integral converges, we will simply write integral a to infinity f less than infinity. That this simply means that the improper integral exists. That is what, that is a easier way of writing it than writing the full phrase. Now the theorem, the first basic theorem in the theory of improper integrals is integral a to infinity f of t dt converges if and only if, given any epsilon greater than 0, there exists a t naught such that absolute alpha beta ft dt is less than epsilon whenever t naught less than alpha less than beta, and I am going to call it Cauchy's principle of convergence. What is the Cauchy, what are other forms of Cauchy's principle of convergence? Let us say for a sequence, what would be the Cauchy criterion for convergence? A sequence converges if and only if it is a Cauchy sequence. Every convergent sequence is Cauchy, that is very easy. Conversely, every Cauchy sequence converges. That is a non-trivial theorem in analysis. Everybody knows this theorem? Okay. So let us, and this is the analog of that for improper integrals, correct. So this is, let us refer to this as the Cauchy's principle of convergence. Okay. So of course there will be a necessary condition and there is a sufficient condition. Necessity is left as an exercise for you to do. Let us prove sufficiency. So how do you prove the sufficiency? You have to show limit t tends to infinity a to t f of t dt exists, some limit exists. How do you show that some limit exists? Use a sequential characterization. every time there is a sequence Tn going to infinity, the corresponding sequence integral a to Tn ft dt, that should also converge to the limit, to a certain limit L, and the L should not depend upon the sequence Tn chosen, correct? You recall the sequential characterization for limits, right? What does it mean to say that limit of f of x as x tends to a equal to L? Xn for every sequence xn converging to a, the corresponding sequence f of xn should converge to L, L, not f of L, L, limits. So now what are we going to do? Take a sequence Tn going to infinity, correct? What does it mean to say that Tn goes to infinity? Now, and there is a T naught given any T naught, Tn will exceed T naught beyond N naught, correct? Let Tn go to infinity and let epsilon greater than 0 be arbitrary. There are two things here. First, Tn going to infinity, and then you take an epsilon greater than 0 arbitrary. Now, epsilon greater than 0 is arbitrary. Now, the statement of the theorem gave you a T naught, right? The theorem says that given any epsilon greater than 0, there is a T naught such that absolute value of integral from alpha to beta f of t dt is less than epsilon whenever alpha and beta exceed T naught. So, given any epsilon greater than 0, the theorem gives me the statement of the theorem gives me a T naught. Now, given that T naught, there is an N naught such that for n bigger than N naught, Tn bigger than T0, correct? So, all this is wired up, okay. So, then what is the integral of Tn to Tm ft dt? That mod will be less than epsilon, that is a hypothesis in the theorem. There is a hypothesis in the theorem because Tn and Tm will exceed T naught, correct? Which basically means what? That can be rewritten as mod of integral a to Tn minus integral a to Tm is less than epsilon. So, take this integral from a to Tn ft dt, that is a Cauchy sequence, and so it converges. Let us call its limit L. Now, what is our next job? Our next job is to show that this L will not depend upon the sequence Tn chosen. That is the thing that we have to show now. Okay, so let us proceed to show that. Suppose you take Tn prime and Tn double prime are two sequences. Tn prime and Tn double prime are two sequences both going to infinity such that limit of n from a to Tn prime ft dt is L prime, limit n a to Tn double prime ft dt is L double prime. Then we have to show that L prime equal to L double prime. There is one trick and only one obvious trick. You interlace the two sequences together. T1 prime, T1 double prime, T2 prime, T2 double prime, T3 prime, T3 double prime, and this interlaced sequence call it Sn. What does Sn do? That also goes to infinity, correct? So, but then integral a to Sn ft dt will have a limit, correct? We have just proved, na? Every time Tn goes to infinity, integral a to Tn ft dt has a limit. Now, this Sn goes to infinity, so integral a to Sn ft dt must have a limit, and so all its subsequences must have the same limit, and then you have the two subsequences, no? A to Tn prime and integral from a to Tn double prime, and these subsequences are converging to L prime and L double prime. So, L prime equal to L double prime, you are done, finished, the job is over, correct? So, we have proved the very important theorem. We have formulated a Cauchy's principle of convergence for improper integrals. But remember that we were able to prove it very easily because we relied on a very deep theorem in analysis, namely we have used the fact that every Cauchy sequence of real numbers converges. That we cannot short circuit. Somewhere the hard work has to be done. That is basic, that is fundamental. The fact that the real number system, the real line is Cauchy complete is very fundamental. You simply cannot get away. Okay. Once you prove that, then everything else is easy. And the interlacing argument is very standard. Okay. Now let us prove the following theorem. Absolute convergence implies convergence. This theorem can be stated in very simple terms, in words. Absolute convergence implies convergence. Right? You have probably seen this in the context of infinite series. An absolutely convergent infinite series converges. That you have seen. And the proof of that is also very straightforward. It is a simple application of Cauchy's principle of convergence. For infinite series, the same result is true, and there you prove it using the Cauchy criterion, the Cauchy's principle of convergence, right? And the same proof will work here also. And so it is left as an exercise. The result is quite reminiscent of the corresponding result in the theory of infinite series. However, okay, so and the proof is left as an exercise. Proof is an exercise. Proof of the theorem. Correct? I think in the previous slide also I wrote it as an exercise and I wrote it as tutorial 5, but I am repeating it here. The result is quite reminiscent of the corresponding result in infinite series. So there are analogies between the theory of infinite series and the theory of improper integrals. But these analogies must be taken with some caution. Some caution must be exercised when you take these analogies seriously. But certain results which are true for infinite series are plainly false for improper integrals. The most basic result in the theory of infinite series is what? If sigma an converges, then limit of an as n tends to infinity is 0. The corresponding result for improper integrals will be if integral of fx dx a to infinity converges, then f of x must go to 0. This result is false, completely false. And the example, counter example is here. Integral 0 to infinity sin of x squared dx and integral 0 to infinity cos of x squared dx converge, as we shall see later. But limit x tends to infinity sin of x squared does not exist. So certain results carry over from the theory of infinite series to improper integrals, certain other results do not carry over. So you should be careful. So just do not argue by analogy and stop there. You have to prove things. Okay. So let us a terminology. The terminology is here. If integral a to infinity converges, ft dt converges, but the a to infinity mod ft dt diverges, then we say that a to infinity integral ft dt converges conditionally. Terminology is borrowed from infinite series. And the classic example of a conditionally convergent improper integral is integral 1 to infinity sin x upon x dx converges conditionally. This is an exceedingly important result. And this improper integral is going to appear in the theory of Fourier transforms, Fourier series and many other places. Not exactly this, the integral that you will see in those contexts will be 0 to infinity, but I have taken it from 1 to infinity just for convenience. The other piece, integral sin x upon x dx from 0 to 1, that is the proper Riemann integral. Sin x upon x is a continuous function. At the origin you define it to be 1. It's a continuous function on the closed interval 0 to 1, and then nothing more need be said about what happens in the range 0 to 1. So let us just focus on the range 1 to infinity. So we are only discussing convergence or divergence, we are not computing the actual values here at this moment. So first let us show it converges. To show it converges, work in the range from 1 to t sin x upon x dx. Integrate by parts once, just once. What do you get? Cos 1 minus cos t by t minus integral 1 to t cos x upon x squared dx, right. One integration by parts gives you integral 1 to t sin x upon x dx equal to cos 1 minus cos t upon t minus integral 1 to t cos x upon x squared dx. What next? We have to examine whether the limit as t tends to infinity exists. There are 3 terms on the right hand side. First term is a constant. The second term cos t upon t obviously has a limit as t tends to infinity. And the third thing is suspect 1 to t cos x upon x squared dx. We have to be careful about the third term and we have to show that the limit for the third term exists. In other words, we have to show that integral 1 to infinity cos x upon x squared dx converges. That is what we are supposed to show. It is enough to show that integral 1 to infinity mod cos x upon x squared dx is convergent, because we have proved that absolute convergence implies convergence. Alright, so that means that we have to show, suffices to show that limit, suffices to show the limit as t tends to infinity 1 to t mod cos x upon x squared dx exists, correct. Now look at the function integral 1 to t mod cos x upon x squared dx as a function of t. What you are integrating is non-negative, and as you integrate over a larger and larger range, it is going to become, the integral is going to get larger and larger. So, it is a monotone increasing function. So, to show whether it has a limit or not, all that you have to do is to examine whether it is bounded or not. So, let us show it is bounded and we will be done. So, integral 1 to t cos x upon x squared dx is less than or equal to integral from 1 to t dx upon x squared, and that you can actually calculate, it is equal to 1 minus 1 over t, which is less than 2, and so it is bounded and the job is done. So, the integral sin x upon x dx 1 to infinity is convergent. That is all very easy. Now, the clever part is to show that the thing converges conditionally, that it is not absolutely convergent. Have you seen this example any time before in the theory of infinite series? It is delicate. The point is that the integral of sin x upon x dx 1 to infinity is delicate. I do not know whether you have studied Lebesgue integration. This phenomenon will never appear in the theory of Lebesgue integration. In the theory of Lebesgue integration, integral of f is finite if and only if integral of mod f is finite. So, the theory of improper Riemann integrals and the theory of Lebesgue integrals are somewhat different. Lebesgue integral is in some sense robust, and there is a certain fragility in the theory of Riemann integrals. Improper integrals are fragile things. Unfortunately, most of the interesting integrals and important integrals that you will encounter in the theory of Fourier series and Fourier transforms will be conditionally convergent. Interesting Fourier series will always be conditionally convergent. There is a very, the theory of Fourier series is exceedingly delicate. But what is very remarkable is that one uses Lebesgue integration to analyze Fourier series in harmonic analysis. A very robust machine is being used to perform a very delicate operation. So, this is a very paradoxical, but that is life, and that over the past 100 years mathematicians have developed this, and there is no other, there doesn't seem to be any other alternative. A centuries experience shows that there doesn't seem to be any better alternative. So let us show that integral 1 to infinity mod sin x upon x dx diverges. Well, it suffices to show that the integral from pi by 6 to t mod sin x upon x dx is unbounded, correct. Once again, you are taking something non-negative, and so showing that the limit exists is equivalent to showing boundedness. And instead of 1 to infinity, for convenience I have taken pi by 6 to infinity, doesn't make any difference, correct. So pi by 6 to t. Now what we do is that instead of t I will take some other convenient number which goes to infinity, and I will show it's unbounded, right. So notice that sin x is bigger than or equal to half on the intervals pi by 6 to 5 pi by 6, pi plus pi by 6 to pi plus 5 pi by 6, etc. Is it correct? Sin x, sin pi is sin 0 is 0, sin pi is 0, sin of x is sin of pi minus x, correct. So sin starts from 0 and finishes at 0, and is symmetrical about pi by 2. The graph is symmetrical. So between the range, so from pi by 6 onwards it becomes greater than half, and it remains greater than half until 5 pi by 6 when it dips down. So is it correct? And since mod sin x is periodic with period pi, sin of x plus pi is minus sin x, but the moment I take the modulus, it becomes periodic. So what is the graph of mod sin x? It's a bunch of arches. In the next slide I will show you. Here it is. You have a bunch of arches here, 0 to pi, pi to 2 pi, 2 pi to 3 pi, 3 pi to 4 pi, and I chopped off these things at a level, at the level half, correct. And so here I am looking at this, interval pi by 6 to 5 pi by 6. In this interval, the value of the sine function is bigger than half. In this interval, it is bigger than half, and so it goes. In this interval, it's bigger than half. That's all I'm saying. Okay. So let's go back to the previous slide. So what I'm saying is, on these intervals pi by 6 to 5 pi by 6, pi plus pi by 6 to pi plus 5 pi by 6, the mod sin x is bigger than half. So let us integrate it from pi by 6 to n pi plus 5 pi by 6. This whole range of integration I am breaking up into pi by 6 to pi, pi plus pi to 2 pi, 2 pi to 3 pi, 3 pi to 4 pi, etc. It's anyway. Now what I'm integrating something that is positive, correct. So from 5 pi by 6 to pi I am not interested, and I throw it away, and from pi to pi plus pi to pi by 6 also I am not interested. So I am only going to integrate from pi by 6 to 5 pi by 6, pi plus pi by 6 to pi plus 5 pi by 6, and so it goes. I am going to get something which is smaller, obviously, because I have thrown away some of the intervals in the middle. Is it clear? What is the first inequality clear? Now look at this inequality. Mod sin x is bigger than or equal to half. So half comes out, and I am just left with integral sum j from 0 to n, integral j pi plus pi by 6 to j pi plus 5 pi by 6, 1 over x dx. Now 1 over x is going to be decreasing. X is going to be less than j pi plus 5 pi by 6. So 1 over x is going to be greater than 1 over j pi plus pi by 6. So here I can replace this by, I can say it's greater than or equal to half summation j from 0 to n integral j pi plus pi by 6 to j pi plus 5 pi by 6. What do I replace? Dx upon j pi plus 5 pi by 6 straight away as a constant. Now I can pull it out of the integral. You do that, you pull that out of the integral, fine. So that's what in the next slide. So 1 over mod x is bigger than or equal to 1 over j pi plus pi by 6, which in turn is bigger than 1 over j pi plus pi, that 5 pi by 6 can be replaced by pi, right. So all in all, integral from pi by 6 to n pi plus 5 pi by 6 mod sin x upon x dx greater than or equal to this half. You understand where it comes from, all right, and this 1 over j pi plus pi you understand. Now what is this 2/3 pi? You have pulled out everything from the integral sign. So your integral will simply be the length of the piece, no? Pi by 6 to 5 pi by 6. What is that? 5 pi by 6 minus pi by 6, which is 4 pi by 6, which is 2/3 pi. That is the 2/3 pi which is there. Correct? And so everything nicely cancels out. You get 1/3 times sum j from 0 to n 1 over j plus 1. You get the harmonic sum, and the harmonic sum goes to infinity as n tends to infinity. So the integral from pi by 6 to t mod sin x dx upon x is not bounded. So the improper integral diverges, and so you get the conditional convergence. All right. All right. So let us stop here today for the first lecture. We will continue from where we left off.